So hello guys, welcome back to my channel. Today we are going to discuss the Basel problem, and the Basel problem is like this. We have to evaluate the sum as n goes from 1 to infinity of 1 over n squared. And so to start, we are going to look at the Taylor series expansion of the sine function. So guys, this is the Taylor series expansion of the sine function. Now we are going to see what are the roots of this function. Sine function is a well-known function, and the roots of this function are etc. So 0, pi, 2 pi, negative 2 pi, these all are the roots of the sine function, and in general n pi for n belonging to the set of natural integers. So for every n belonging to the set of integers, if we put all the integers into the n with the pi, we will get all the roots of the sine function. Now we are going to divide this whole equation by 1 over by x. So this is the infinite series expansion of sin x over x. Now we are going to see what are the roots of this function. The roots will almost be the same except this 0. And why this is the condition? Because at the point x equals 0, there is a 0 in the numerator and a 0 in the denominator, so it is kind of undefined. But if we take the limit of this expression as x goes to 0, then it converges to 1. So obviously in this case 0 cannot be the root. So I will rub the board and we will continue. So far we have reached this point. Now we are going to do a substitution. We are substituting x equal to square root of t. So if we substitute square root of t here, this all are even exponents. So the square root will cancel with all of the numbers and we would be left with 1, 2, 3, 4, etc. So this is the infinite series expansion of this function. Now we are going to investigate what are the roots of this function. So the roots of this function will also be the roots of this infinite series. So if we investigate this function, the roots of this function would be as follows. So pi square, then 2 pi whole square, then 3 pi whole square, etc. will be the roots of this function, and these are exactly the square of the roots of this function. We have saw that the roots of these functions were pi, negative pi, 2 pi, negative 2 pi. So we substituted x is equal to square root of t, and square root function has its inverse function as x squared. So we have to square all the roots. Therefore, the roots of the function, this function will be this. In general, n squared pi squared. Here n will not belong to the set of integers. It will belong to the set of natural numbers. So this is it. Now we are going to apply our special theorem that we have discussed in a previous video. So you can see that video by the link here, the white box. Click on it and see the video, and it is not so long, and then come here because we are using that theorem here. So by our special theorem, the coefficient of t here, the variable here is t. So the negative, first we put the negative sign, then the coefficient of x divided by the constant term. And according to the theorem, it will equal to the sum of the reciprocal of all of these roots. So it will equal to the infinite sum. We are assuming this as a polynomial. Here you could see that we are assuming this as a polynomial of infinite degree, and this function satisfies all the conditions of a polynomial. All the powers of t are natural numbers, and so all the conditions here are satisfied. So we could safely take it as a polynomial of infinite degree, and now here we will get the sum of the reciprocals of all of this root. So this will equal to the sum n going from 1 to infinity of 1 divided by n squared times pi squared. So I will rub the board and we will continue it again. So far we have reached this point. Now we could simplify this a bit. You could see that we are almost there, just a pi is there here. So we could simplify and we could get it easily from this point. The left hand side simplifies, the negative will cancel, and this 3 factorial evaluates to 6. Therefore the LHS will be 1 divided by 6, and it will equal to the sum. So the pi square here is a constant, so we could multiply both sides by pi square, and we will get pi square over 6 equal to if you multiply here pi square, the pi square in the numerator and the pi square in the denominator will cancel each other, and so we would be left with 1 divided by n square, and this is exactly the answer that we wanted. So we have solved the problem that the infinite sum of n going from 1 to infinity of 1 divided by n squared equals pi squared over 6. So this was a wonderful proof. Thanks for watching the video.